Okay. Hello, everyone. Welcome to Physics 2048, Physics for Engineers and Scientists 1. So the way we're going to be doing this today, for those of you online, the slideshow is available on the screen. It's also available for you to download on the UCF SARC Study Union website. I also have a separate slideshow that has all of the answer keys. What we're going to do is, for those of us in the room, we're going to spend about 8 minutes on each problem. We're going to try to solve it on our own, and then we're going to go over it, okay? So I'm going to go ahead and jump right into it. So we're going to start out at the beginning of the semester. The most simple material that we went over was the kinematic equations. We have equations of motion that don't take into account what it is that's doing the moving, okay? And so you can see we have two sides on this slide. We have V equals V naught plus AT, and the other side we have theta. So we learned about two primary things in this class. We learned about motion in a straight line and at a vector angle. And we also learned about angular motion. We learned about angular momentum, angular velocity, angular acceleration, torque, all of these things. And we're going to cover them today. Okay? So these formulas are available for you throughout the demonstration if you need access to them. Remember, you probably have a formula sheet on your exam, so you don't necessarily have to remember all of these things. So we have force and we have torque. One of them is an angular version of the other one. All right, we have some equations here. We're going to go quickly through these equations and we're going to get right into the problems, okay? I can go back to these equations at any point if you feel that we need to. So we have energy and momentum equations here. We have the conservation of momentum. That tells you that the momentum at the beginning is the same as the momentum at the end. This is a very fundamental and not very difficult principle to understand, but it's important to remember because it'll let you solve a lot of problems. Okay? So with that, let's go to the first problem. Can you read that? I can make this so that we can read it. Can you guys read that now? Yeah? All right, that's the picture, and that is the problem. I wish I could full screen this, but I'm not sure I can because this is not I'm not logged in on this computer. Sorry about that. Again, this is available online if you just want to have it in front of you. But go ahead and take a moment to try to solve this problem. Hi, are you here for Physics for Engineers? All right, welcome. I'm David. I'm the one doing the presentation. So if you guys are here for Physics for Engineers, go ahead and have a seat. We're currently working on the problem that's on the board. These problems are available on the SARC Study Union WordPress site. So if you want, you can get them in front of you. We also have the answer key will be available on the WordPress site. So if you need to look at this after, maybe we don't finish, maybe you don't understand one, you can go back and study it as much as you want, okay? Thank you for that. for those of you in the room, if you finish, go ahead and let me know. Or if you feel like you have no idea how to begin, you can let me know that as well, so I know when to stop waiting. All right, who's still working? Is anyone finished with the problem? Anyone have any questions? Anyone lost? I'm getting a lot of not any answers. So nobody's still working, but nobody's done either. Okay. Use your words. All right. So, can I zoom in on this? So, the first thing I do in order to solve this problem is I start by making a little diagram. You can't really see this very clearly, so let me redraw it a little bigger. All right, so the things that we're given the initial velocity, we're given the distance, we're given the angle theta, and we want to find the height. So the first thing we know is that velocity is equal to distance over time. Okay, so the velocity in the x direction can be found by using this formula here, where vi is equal to cosine theta. We know how far it's going to travel in the x direction. It's d. So we can use this equation to solve for how long it's in the air. So once we get to that point where we have t, we're going to calculate the position in the vertical direction. All right? Vyi times t is 1/2 a t squared. Now, we know what a is. A is negative 9.8 meters per second squared. So, Vy is equal to Vi sine theta. And t, well, we have t. So let's plug that in. Vi sine theta squared. Are there any questions about how I got to this point? All right. Well, so at this point, we're just going to plug in the numbers that were given to us, if we were given some numbers. And we're going to solve for h. In this case, we don't have numbers, but we can still solve it algebraically. D tan theta, okay, so sine over cosine, and V over V, right? This is going to cancel. So d tan theta minus 9.8 d squared over 2v squared cosine squared theta. Who got that answer? Yeah? All right. Are there any questions on that? Was that a question or was that a I got that answer? Yeah? Good. Okay. So we're going to go ahead and go on to the second problem, okay? you here for Physics for Engineers? Physics for Engineers 1? Sorry? I don't know, but here we are.
Okay, is there another session going on?
Session of what?
Physics 1?
Not to my knowledge.
Are you David H?
Yep.
Oh, okay. All right. Yeah.
I'm sorry about the inconvenience. So for those of you who are new, these slides, as well as the answer key to the problems on these slides, are available on the UCF SARC Study Union WordPress site. You can find the questions and the answers there, okay? Go ahead and let me know if you're finished or if you're stuck. Is anyone still working? All right. So if you're new, these slides, the questions and answers are available on the UCF SARC WordPress. I'm about to go over this problem, but why don't you take a quick moment just to read what the problem says so that you're not lost, and then we're going to go over this problem. All right, I'm switching to the .cam now. So once again, I started with a diagram. I noticed that my rock resembles a circle. Okay, so I have the formula of kinematics for the y direction. It has an initial position, no initial velocity in the y direction, and an acceleration caused by gravity. And in the x direction, it has no initial position and no acceleration, only a velocity, vi. All right, so this equation right here, I simply took this equation and I manipulated it a little bit to solve for y. Now, we have this equation. This is the equation for a circle, right? Y squared plus x squared equals r squared. This is to give us the position of the rock. The question asked us to ensure that the ball is higher than the rock at all times. The question says we have to make sure the ball doesn't hit the rock. So we know that the height of the ball has to be greater than the height of the rock. So that allows us to get this equation right here. Right? This one is equal to r squared. This one is greater than r squared. Now we are going to take this equation for y. We're going to substitute it in over here. Now from there, I just did a few steps of algebra. I FOILed out my own quadratic there. And that was the answer that I got. Raise your hand if you got that answer. Raise your hand if you have any questions about what I did. Okay. So now this question had a part B. What did part B say? With this initial speed, how far from the base of the rock does the ball hit the ground? So, when the ball hits the ground, y of b is equal to 0. So if we have 0 equals r minus we have that. X minus r equals radical 2 minus 1 times r. All right, so that was actually a much shorter step than the first part. Yes? X minus r equals radical 2 minus 1 times r. That's the distance from the rock's base. You need me to show it again? Sorry about this. It's that. Hello, this is Physics 2048. All right. Who's ready for it to be gone over? All right. Raise your hand if you finished. Raise your hand if you have no idea what to do. Raise your hand if you're sitting politely and not doing anything and waiting for me to tell you how to do it. All right, here's how to do it. So, we have components. We were given numbers this time. It was a little different from the other problems because of that. We have a x velocity, and we have a y velocity, and we have an angle. So it is not that difficult to calculate the initial x velocity and the initial y velocity. From there, we have our kinematic equations. We have that the final y position is equal to the initial position plus the velocity times time plus 1/2 at squared. We have a whole bunch of these values already. This one's a little small. Vyi equals 10. Vyi, the velocity, is 10. The initial position is 0. The end position is -45. And the acceleration is gravity. The only thing we don't know is time. So that's what we're going to calculate first. Now, we set this problem up, okay, and we can use the quadratic equation to calculate the time. Now, you're going to get 2 zeros here, but one of them is negative. Does it make sense to have a negative time? Well, no. So we're going to go with this. Who got that? All right. So that's part A. Once we have time, we're going to use this other kinematic equation to find the final velocity. Now, the final x velocity, it didn't change, but we have to find the final y velocity. We're going to use our initial y velocity, and we're going to use our acceleration to calculate that. This was a simple plug and chug, okay? Time is 4.22. 10, that's from before, 9.8, gives us that. We have that. Now, when you have the x and y components of something, what you have to do is you have to use the Pythagorean theorem to find the total magnitude of the velocity. All right. Are there any questions on that? Sorry? Scroll it like this. Yes. Which part are you wanting to see? That's a 45. Sorry, my handwriting is not great. All right. Is everyone good? All right. I'm going to go into the next problem. Sorry, say again. VF. Remember that the negative sign goes away when you square it. All right, so we're moving on from kinematics. We're going to talk about some rotational motion in this problem. All right, who's finished with this problem? All right, is anyone not ready for me to go over it? All right, we're going to go over this problem now. So, the first part of the problem said, given the initial velocity at radius r initial, solve for the velocity at some other radius. So in order to do that, we're going to remember that momentum is conserved. Okay? So we have angular momentum given by mRV, and we simply solve for Vf algebraically. Okay? So that step, does anyone not understand what I did there? Question? So I used the equation, I guess it's kind of hard to see. Let me write it larger. M RF VF equals M RI VI. I canceled out these. Okay, so remember, we know this, this, and this. Okay, so we just solved for VF equals RI VI over RF. Question? Sorry? Yeah. All right. So, once we know the final velocity in terms of the initial velocity, we are asked to find the tension. All right, so tension on the rope is equal to the centripetal force on the puck. So we have mv squared over r. All right, we plugged in for Vf squared. I know this is hard to see. I wish there was something I could do about that. I'll try to write bigger from now on. So Vf, we plugged in the Vf from part 1 into this equation, and we got this simplified to this. All right? So remember, Vi, Ri, and Rf are in theory all known constants at this point. Okay, so we've solved for tension algebraically. The next part of the question asked us to calculate the work done. So work is the measurement of the amount of force done over a motion. Okay, the integral of f dot dl. Fortunately for us, tension is a kind of force, right? So we're just going to plug in that. And we're going to integrate with respect to r. Now looking over here, Ri, r initial, this is a constant. This r right here, this is not a constant. This is an r. This equation would hold for any value that we're going to integrate to, right? So however much we move the string, we're going to plug that in for Rf, that's the bound, and we're going to integrate with respect to r, okay? We get this, which simplifies to this. Are there any questions so far? All right. The very last question was to simply plug in and find some numbers. These are the numbers I got. Does anyone disagree with these numbers? All right, who's ready to go over this problem? So the first thing that it asked us to do was to draw some free body diagrams. So this is what mine looked like. I drew all three of them separately, and I tried to account for all the forces that are acting on these bodies. So each of the hanging bodies, they have the force of gravity, and they also have tension from the cord. Now the one in the middle is the most complicated because it has both tensions pulling it, it has gravity, it has normal force, and it has friction. So we know that because one of these masses is larger than the other mass, we know what direction it's going to be moving in. So we know that friction is always opposite the direction of motion. So I drew my arrow right there. Okay? Now, we got some equations for the sums of the forces because we remember that F equals ma. The sum of the forces equals mass times acceleration. And we know the masses. So we presume that because m1 is bigger than m3, the system rotates like this. m1 is going to go down, m3 is going to go up, and m2 is going to go that way. Again, like that. So we decided to say, well, that means that the force on m1 is going to be negative. Okay, the force is equal to negative ma. The force over here is going to be positive m3 times a. And here, we're going to just say that that's negative as well. Okay? Now, all of these forces, these are the sums of the forces, right? So you add these together to get that. You add all of those together to get that, and add these together to get that. Now, we don't know what all these forces are, but we know their relationship to each other, and we know that if the masses are all connected as a unit, they're going to move at the same pace. So the acceleration a is actually the same a. It's the same a in all the cases. So what we actually have is a system of equations over here. And so we're going to solve this system of equations. I used the method of elimination. You could technically use substitution, but this one happens to work out very nicely with elimination because we have tension 1, negative tension 1, tension 2, negative tension 2. So if you just add all of these together, all of your unknowns cancel out except for a. Right, this is 1 technically because this is mass, acceleration, mass, acceleration, mass, acceleration. So when we plug in numbers, that's what we get. We get an acceleration of 2.31 meters per second squared. And then we simply go back into those equations that we already found and we solve for the tensions that way. We plug in for A. Plug in for A. Are there any questions about anything we did here? Yeah.
Formulas. How do you know like which one? I know that this is what you have to solve for M1, M2, and M3, and that's it. And then, how do you find these?
How do you find these equations?
Yeah.
These equations?
Mhm.
Okay. I'm going to go over that, but I'm going to go over it on the screen. Okay? All right, so I was asked the question, where did these formulas come from? It seems like a bit of a jump. Well, fair enough. Let's go over it further. I'm going to flip over to here. Okay, so we know that the sum of the force is equal to mass times acceleration. This is one of Newton's laws, right? Now we're going to apply this for all three masses. So looking at our diagram again, let's look at M1 first. There are two forces on M1, and they're going in the opposite direction, okay? So we're going to say that the tension force, which is in the upward direction, that's positive, and then mass times gravity, okay, that's going to be the sum of the forces, okay? The force plus the other force is the sum of the forces. It equals mass times acceleration. Now, mass, what is the mass of the first body? I don't actually remember the number. I have to look. Is 1? It's 4. Okay. So 4 times 9.8. That is how we got 39.2. All right? We just calculated this force and this force, and we added them to get mass times the acceleration. This is not the acceleration due to gravity. This is the acceleration that the thing actually moves at. Okay? This is g, the acceleration from gravity. It's the downward force component. Okay? So I'm going to repeat this process. I'm going to look at the third mass, 2, 3 minus m3g. So if we look at that, m3g, 2, 3. Okay. But now this one's going to give us a positive answer because we know the direction, okay? This is going to go up. We know that this is bigger than this. So that's where this comes from, okay? 2a. 2 is the mass. 9.8 times 2 equals 19.6. All right? And now the middle body is the most complicated because we have the most forces to add. Now, so look back at that. We have all these forces. We're going to make this easier on ourselves. Before we add up all 5, we're going to notice that m2g and normal force are going to cancel. We know that m2 is not actually moving up or down. So we're going to add this, this, and this. All right. Now you were given the coefficient of friction, which is 0.35. Now we calculated the normal force. The normal force is the opposite of mass times gravity, right? Okay. Mass on this block is 1. Okay. So that's why this is a 9.8. This could say 9.8 times 1 if we want to be correct, because that is mass times gravity. Mass is 1. All right. Does this answer your question as to how we calculated each of these 3 equations? Do you get it? Which t?
For the first one?
How come that t is not negative? You mean?
Like, mg is bigger than
You're talking about this now? mg is bigger than the first t. That it is, and this is negative. I just didn't write it right. Good catch. Okay, this one is negative, 2 is negative, 3 is positive. Okay, negative, positive, negative. All right? Okay. Are we ready to move on to the next problem? Yeah? All right. Great. Excuse me. All right, who's ready to go over this problem? All right, well, we're gonna. So, first, actually, before you look at my notes, let's talk about what an elastic collision is versus an inelastic collision. Does anyone remember what those words mean? An elastic collision is a collision where kinetic energy is conserved, okay, throughout the collision. So, now that we know that, let's look at this. So, we have the mass, the gravity, and the height at the top. And we have the fact that when it rolls down, the potential energy goes to zero. This is potential energy, right? potential energy goes to 0. At the top, kinetic energy is 0. So all of that potential energy gets converted to kinetic energy, which means that m1gh at this point is equal to 1/2 mv squared at this point. All right? So mass 5, height 5, gravity 9.8. So we can plug that in. We can get that. Okay? We solve for v, because that's what we want. Radical 2gh, 9.9. All right. Now, because energy is conserved, we have this equation for the speed after the collision. All right? I should probably label that. This right here, V1 final. That's what that is. Question. So this equation comes from conservation of energy. Okay? So I don't have that in my notes, but I was trying to work it out because it occurred to me that somebody might ask. So we have that initial in 1, initial in 2 equals initial, or final in 1, final in 2. Now remember, the second one starts at rest, so gone, okay? And I got a little tripped up in my own math, and I don't want to show you wrong stuff, but I can tell you that if you take this heinous thing and manipulate it, you will get this, okay? You had to solve for V1F, and that is what we're going to get. So once we know the final velocity, which is 3.3 meters per second, what we're going to do is we're going to go back up to mass times gravity times height, okay? 1/2 mv squared. This is the energy after the collision. All right, we're going to take this velocity, we're going to take this mass, because the mass did not change, calculate the energy after the collision, plug it into the potential energy to find the height. Are there any questions on that? Yo. Yeah. We could use conservation of momentum. If this were an inelastic collision, that would mean that energy is not conserved, right? So we would have to use momentum. We couldn't use energy. It would be wrong. So they might test you on your understanding for the word elastic and inelastic, okay? The important thing is to remember that elastic means that the energy is conserved. It is possible that you could have solved this with momentum just fine. I'm not actually sure. I don't want to say for sure, but I don't see why it wouldn't, because momentum is conserved. All right, we're going to move on to the next problem, okay? Oh, geez, sorry about that. I should probably show you the problem in order for you to do the problem. Was that a question? Or no? Okay. All right, who's ready to go over this problem? All right, I'm going to go over this problem. This is not a very long one. So, all right, so we know that at the start we have a velocity of 40, and we know that this velocity has x and y components. We know that the x component does not have an acceleration after it leaves the bat, okay? So we know that at the apex, the x component of the velocity has not changed. However, the definition of apex, right, is that you reach the point where you're no longer going up and you're starting to go down, okay? So that means that the vertical velocity is 0. So now we can use the x component of the velocity by itself to find the total magnitude of the velocity at the apex, which is given right here by the equation 1/2 mv squared. Now, the mass was given as 0.15, and we're going to plug the velocity into that equation to get our answer. Now, if we wanted, we could pretty easily also find the initial energy and find the change in energy. But the question didn't ask us to do it, so I didn't do that. That one was pretty simple. Does anyone have any questions about that? No, okay. I didn't think so. Can you pass those? So while you're looking at this problem, I'm passing around some surveys. You can use these to go ahead and tell me if I was helpful, or maybe if you didn't think I was helpful today, you can tell me that too. If you have complaints about something other than the session itself, like maybe the random room change, you can feel free to complain about that. Thank you for filling these out. Even if you have nasty things to say about me, I want to hear it. Thank you, guys. We still have about 20 minutes, but I wanted to give you those now. All right, who's ready to go over this problem? All right, I think we're going to go over this problem. Was this one a little more challenging? Yeah? All right. It certainly was a little longer. So the way I went about solving this is I used the conservation of energy. All right, now this is not actually a complete equation here because we have to use Hooke's law because there is a spring. All right, and the energy in a spring, 1/2 kx squared, 1/2 kx squared, that's x final and x initial. This k, that is your spring constant, okay? So this is our initial first. I can't fit it all on the screen at once. So initially, we don't have any kinetic energy, so we have a 0. We're going to calculate the potential energy. This is from the big block times gravity, mgh, okay? This is 20 centimeters above the ground. So then we have energy in the stretched spring because the spring is stretched up. 1/2 250 x squared, okay? Does anyone not understand anything that I've written up here so far? Question?
When you say that 30-kilogram block is 0.2 above the ground, you mean 0.2 above like equilibrium?
Yes, so at equilibrium, the spring force is going to be canceling the potential, or I guess I should say the spring force is going to cancel gravity, right? And it's not going to move. So, and then we have our final. So we now have 1/2 mass times velocity squared. So we have 50 because both blocks are moving at the end. Okay, and they're moving the same speed because they're attached to each other, but we don't know what that speed is, so we're just going to leave a v there for now. We're going to look at the potential energy. We're going to notice that since the spring is now at equilibrium, Hooke's law tells us there is no energy in the spring, so we just have a potential energy given by this. So this 20 kilograms, that's the small block. The small block that has now risen after being let go to a height given by that. All right, so originally the bigger block went up 20 centimeters, but we don't know exactly how high the little block went because it's on an incline, okay? Now, we're able to use this equation up here to calculate. We got 58.5, and we got 5, okay? And then we got 25 kilograms times velocity squared. We still don't know what that is. Plus 25.2 joules. And then we just solved for V. Do you guys need me to show you how to solve for V, or are we good with that? All right, I'm going to assume you guys know how to solve for V. We've got time for one more. So let's go get right to it. Did either of your classes cover reference frames this semester? If you don't know what it is, you probably didn't cover it. No, okay. All right. I'm sorry. This problem involves a thing that you might not know what it is. And I didn't catch that before. I'll go over it very briefly, but if you weren't taught it, I'm not going to teach it. Just don't worry about it, okay? All right. So we're going to use conservation of momentum. The very first thing that we have is mv. This is m1 v1 plus m2 v2. Okay, all of those are given, so we know an entire side of the equation equals m1 v1 m2 v2. Okay. Is anyone confused on that? No. So there's a thing called a relative velocity equation. You might not know what this is. Don't worry too much about it. v2f minus v1f is equal to 1.9. Okay? So once we have this, if you don't know where this came from, what? What's up? Question?
You said that elastic equations are that have like kinetic energy is conserved.
If this is an elastic collision, then yes, kinetic energy should be conserved as well.
Then how come we use the momentum instead of the elastic or the kinetic energy?
It might be feasible to use kinetic energy instead of momentum if we chose to, but no, it shouldn't matter. No, so momentum is conserved all the time, right? And kinetic energy is not. The reason we used kinetic energy in the previous problem was that we were able to find potential energy and convert that directly to kinetic energy. It was convenient to use kinetic energy. Here, it's not necessarily convenient. So once we have this equation, okay, if you don't know where it came from, don't worry about it, but it's not complicated. And we're just going to solve for v2f is equal to 1.9 minus v1f. And we're going to plug this in up here. All right? So 0.2 v1f plus 0.3, 1.9 minus v1f. So what we did is we got rid of one of the extra variables. Okay, this still equals all of this stuff up here. And now we only have one variable, so we solve, and we get that v1f is equal to negative 0.78. And then we get that v2f is equal to 1.12. Did you do anything on solving for velocities of center of mass? Is that something you did in class? Because this question called for that. Is that familiar at all? No? Okay. We're going to go ahead and call it here, everyone. Thank you guys very much for coming. Don't worry too much about center of mass then. I hope this was helpful. Please leave your surveys at your seat and I will pick them up.